Balamurugan from Minatal Power Systems as a presenters. Like uh, I'm going to coordinate this session. Before going to the technical presentation, so this is the agenda, like introduction to the functions of CIGRE and NGN activities in India and the NGN committee. And after that, we will go into the technical session. So, like, if you want to know about the CIGRE, it is closely related with IEC, as many of you might have known, like International Electrotechnical Commission. So IEC was formed in 1906, like, and later, and IEC was actually like a big organization which covers like electrical and electronics, everything from low voltage to the high voltage. And later people believed that thought that there has to be a dedicated organization for electrical transmission. So that is how SIGRE was formed in 1921. So the aim of SIGRE is to collaborate in an international setting to discuss, study, and bring out solutions to technical issues in relation to specifically related to generation, transmission, and distribution of electrical energy. And the significance of SIGRE, as you might know from this image. So most of the world, most of the countries in the world, like in countries in Asia, Europe, Asia Pacific, and Africa, Middle East, they follow IEC, which is closely related to SIGRE. So that is how it is relevant to us. And these are the 16 study committees of SIGRE under four groups, Group A, which focuses on specific equipments, and Group B, which focuses on the technologies, and Group C, systems as a whole, power system, and then Group D about the new materials and technologies, especially the information technology. These are the 16 domains of study committees of SIGRE. And if you need any further information, you can reach out to us and the below email ID. And over to Aditi, who is the chair of CIGRE NGN India. Hi, Aditi. Aditi, you're on mute, I believe.
Hi, Gopal. Thank you.
Yeah.
Thanks
Yeah,
for
that's
the
fine. Thanks.
introduction, and thank you everyone for joining this webinar here today. As Gopal said, this is our first webinar in India, and I believe we have had idea about IEC and IEEE a lot, but currently SIGRE is also moving ahead in getting a lot of work done in the power system area, and that closely aligns with in the context of India because we follow a lot of standards which are European based. So this is a very good program to be part of, and we would be happy to help you with and getting in contact with the team members here to be a part of the SIGRE group as such. Please feel free to reach out to us at the email we have mentioned. As a next step, this is a new group which we have created within SIGRE India. If you remember, in October of 2023, we had a first kickoff meeting where we initiated this next generation network, basically giving a platform to the young professionals in India, be it from academia or be it from industry, to participate and project their ideas in front of the power system industry as such. And after our kickoff from October 2023, we have created a committee in the International Executive Committee here in India. I am the chair, and I have a group of colleagues who are helping us move forward in this agenda of bringing the young professionals a stage and bring their ideas to the power system industry as such. So you have heard from Gopal till now. He is the webinar coordinator. We also have our secretary from the call today, Shashi. Thanks for joining the call. Then we have our academia coordinator. You may have received a lot of emails or some other inputs from our academia coordinator, who basically tries to bring in more people from the students and academia industry to be part of SIGRE. So Atul, thanks for joining the call. And last but not the least, we have a lot of social media presence. We have a LinkedIn page, which is shown here below, and that has been done. And we have been successful in that because of our social media coordinator, because of Chandan, and now Sarvanan will be also supporting us in this specific area. So this is our team. We work all together. We are looking for more hands here. And if somebody is interested, please feel free to reach out to us. We'd be more than happy to bring you on board and get you in the NGN group in India. To be part of the NGN group in India, one thing which I would like to just point out is you need to be below the age of 35 years, and then you can be part of NGN India. If you are not below 35 years, we can bring you into the CIGRE team as such, and you can be a CIGRE member. For the NGN group, there is some discounts we have for the membership, so you can make use of that, and any of us can provide you with more details. So feel free to put in your questions in the chat function. Uh, Going into the next slide, there are multiple activities we have planned within NGN in India. One thing is, which is today you are attending, is the webinar. We'll have multiple of these webinars hosted. Some may be in India, some may be co-located with other international NGNs, like the next one which we have planned is with UK. So that is one thing which we have planned. Another thing is in the books of doing a technical visit. Once we have a roster completed for the NGN India, we would like to have a technical visit for all the NGN members to one of the sites within India. Third thing is the NGN Showcase. This is a showcase competition which happens every other year in the Paris session for CIGRE. And I'm very happy to announce we have one participant from India who has been shortlisted for the Paris conference, and he is actually going to present on that today as well. And last but not the least, if you would like to get included in a lot of working groups, we have a lot of working groups for all the study committees, which Gopal just mentioned. But also there is the Electra Journal where you can publish your articles. So there are multiple ways to collaborate, and all these are focused on your personal growth and also an involvement in the power system industry with experts from worldwide. So feel free to reach out to us. We'd be happy to put you in contact with the right folks to be part of this amazing team. And also, if you're interested to participate, please put in your name and we'll reach out to you accordingly to move forward from there. Over to you, Gopal. And thank you everyone for joining in today.
Thank you, Aditi. And so today our session is about use of digital tools and technologies for transformer asset management with focus on digital twins. And we also have some sessions planned in upcoming months. So in future of digital substations around July, and there are few sessions also planned for the other quarters of the year. So if you would be interested, please feel free to reach out to us. So you can reach out to my email ID and also to the CIGRE NGN India email ID. And yeah, so welcome to the presenters. So Devnath Jha is a digital initiatives and asset management professional who works in Power Grid Corporation of India. So he has overseen operation and maintenance activities of EHV class power transformers and shunt reactors, notably in reliability assessment domains of EHV class power transformers. And he is a member of a joint working group between A2 and D2. Currently, he is involved in transformer digital twin related activities in CIGRE Study Committee A2, and he is an active member of CIGRE and IEEE, and he contributes to the advancement in transformer asset management. And welcome Sarvan Balamurugan, and he's the founder and CEO of Minatal Power Systems, and he has 11 plus years of experience in different domains of power system, which includes protection system design and commissioning as well. And he is also a SIGRI joint working group member between A2 and D2, which involves the activities of digital transformer digital twin. And currently he holds a master's in power system, and he's pursuing his PhD in transformer diagnostics and digital twin. Thank you both, and over to Saravanan for your presentation. I'm stopping my screen.
Thank you, Gopal, for the intro. Let me
Thank you,
just
Saravanan.
quickly share my screen. Can I get a check that it is working? My screen is visible.
Yeah, yeah, I can.
Got it. Good evening, everyone. Thank you for joining us. Today, like Gopal already introduced the topic, we'll be discussing about the use of digital twins and technology, digital tools and technologies for transformer asset management. Uh, I wanted to start off with talking about the present trends in the transformer industry. What are the recent updates? How the market is? We'll be moving on towards the basics of transformer asset management, like what we so that we are all in the common ground when we discuss about asset management. Quickly wanted to introduce the concept of digital twins. That is a very interesting domain for which I've been working on more than I think 6 years now. So transformer modeling for digital twins, followed by applications of the digital twins for asset management and the future scope, which Mr. Dionath will be taking over. Yeah. So the present trends in of transformers in power systems. Right? So when we talk about transformers in power systems, they make one of the key components in transformers, either for transmitting power between different voltage levels, in distribution, in the generation, in the transmission side, and they are very key equipment when to deliver the power till the last mile, that is to your house and the industries, right? The power transformer market is a very huge market. It's close to a $60 billion market, and it is growing at a fast pace, right? So it is estimated to reach a $110 billion market by the year 2032. Now, this is a interesting piece of information because it shows both monetarily how big the market is going to be, but at the same time going to tell us engineers how big the market is in essence by the sheer number of transformers that is going to be coming into the picture, and over a period of time the maintenance, the operations and the management of such transformers which are going to be coming up into the market over the years, right? And of all the markets, the Asian Pacific is expected to be the largest market by sheer value, and this is mainly contributed due to the high speed or the high increase in the construction, the infrastructure development, the urbanization, and just the sheer population of the people that are concentrated in these areas, right? So we belong to one of the fastest growing markets for transformers. We belong to one of the biggest population countries in the world, and we belong to one of the places where the estimated demand of power is also increasing exponentially, right? So we are expecting a peak demand of somewhere around 369 gigawatt to around 725 gigawatt by around 2036, with an installed capacity of around 1337 gigawatt, right? So this is something that we are forecasting by the year 2036, which is around 12 years from now, right? So if you are considering the growth in the transformer market and the growth in the demand, we are noticing that there are going to be a lot of new technologies that are going to be coming into the picture with digitalization, machine learning, artificial intelligence, and so on. At the same time, we are also are having a responsibility to address the maintenance of the transformer that are already with us and the transformers that are going to be coming into that with the right strategies, right? So by 2032 we are going to be adding around 600 gigawatt till 2032, which essentially means that we need around 600 power transformers at 500 MVA level in the next 5 years, and around 1200 power transformers in the next 10 years, right? Now these power transformers, just by looking at this, you can see that just by looking at the number of transformers in the 500 MVA level, we can already estimate what is going to be the increase at the normal distribution level, right? So that number is going to be huge, and for manufacturers, for utilities, and even for certain service providers, this is going to be a very interesting time to see how these transformers are going to be designed, engineered, and actually operated and maintained, right? So some of the recent initiatives in the technology side in the transformer industry, again split into both the design and engineering side, would involve manufacturing up to the 765 kV level on a commercial basis, and up to 1200 kV level on the trial basis. Lot of manufacturers are introducing the use of continuously transposed conductors and also the thermally upgraded graph paper for winding to better increase the efficiency and reduce the losses while making it stronger at the same time. And one of the interesting point to note is the use of resin impregnated paper bushings in transformers till 400 kV, thereby reducing your partial discharges, your tan delta values, overall improving the lifetime of the transformers, right? We are also using ester oil and gas to liquid or GTL oil as alternative insulation fluids on a trial basis, and focusing on today's topic on the diagnostics and monitoring, right? So we are estimating the use of asset health indexing, health monitoring, health assessments, so many terminologies that have come up in the recent times. Online monitoring systems, use of advanced diagnostics techs like UHF, ultra high frequency partial discharge, frequency domain spectroscopy, so on, right? So these are just some of, just to give you an idea on what our industry is and what in our country, the direction in which we are going, both on a financial as well as on a technical level. Now, let's take a small breather to understand what is transformer asset management, right? So when we talk about asset management, it starts with the purchases, right? It has to start with the planning on what to buy, how to buy, when to buy, and what do you do during the normal lifetime of a transformer, and what do you do after the transformer has reached its end of life, right? So we are always going to be starting with the resource planning, which involves the design and optimization of the transformers, and not only the transformer rating, the transformer location, the transformer load capabilities, and so on, right? And once we have designed and optimized it, let's purchase it, let's place it in the optimal locations and for optimal usage. Now it is time to operate and maintain the transformer, right? So the next step will be talking about the maintenance strategies. So how do we actually maintain it? What are the different preventive and corrective actions we take for transformers? And when you want to optimize the transformers, the lifetime, you want to optimize the maintenance that is being done, we need to talk about performance management. So performance management will give you a much clearer idea of what your current status of a transformer is, what are the best methods you can use to maintain the transformer, which involves assessing the health of the transformer, either by doing the routine test on a time-based basis, or by doing condition monitoring either on an offline side or on an online real-time condition monitoring, right? So as the transformer life increases, right, so we have to focus, we will be starting to focus on the reliability evaluation. We'll be evaluating how good the transformer is, what is its reliability level with respect to outages, is there any strategies that has to be done, or maintenance that has to be done to improve the transformer lifetime, right? And once pushing the transformer to its limits to the end of life, we need to understand about how or what needs to be done with the transformers at its end of life, right? So we obviously will be going for newer transformers, but what do we do with the older transformers? So regarding the scrap management, regarding the asset management at the end of life, needs to be discussed when we are talking about asset management, right? So all of this kind of comes as objectives of asset management. And today's focus will be on the digitalization and the maintenance strategies. So the maintenance strategies, like you can see over here, so you are going to have a time-based maintenance and a condition-based maintenance, right? So if you're looking at the maintenance strategies for a distribution transformers, right now most of the utilities have this kind of run to fail model where you are just going to wait till the transformer fails, and once it fails you're going to replace it. But this strategy will not be suitable for something that is at the generation or the transmission level, right? So the strategies have to be tailor made to the location, to the usage of the particular transformer. So here you can see certain time-based time-based maintenance strategy that will give you a preventive maintenance. These are your scheduled tests that you do, the routine test that is being done based on certain time-based interval, right? Now, condition based strategies are something that has come up quite a while back, where you determine the condition of the transformers either based on some routine test or by online monitoring or health assessment, and you can either do a preventive maintenance during a scheduled time, or you do a kind of you move towards predictive maintenance while while working in hand with prognostics and health management, right? So when you want to predict the health of the transformer, you want to predict what maintenance has to be done for the transformer based on certain conditions and based on certain prognostics or diagnostics that are being done, then it comes under predictive maintenance. So the preventive and predictive maintenance kind of come before the failure of the transformer. So once the transformers have failed, then you work on making the corrective actions. Like you identify, you diagnose the problem, you identify what are the issues, you identify the right fixes, and you correct them. So these are just some of the maintenance strategies that are being used right now, right? And if you're looking at data, this was way back in 2015, done by the Transformer Reliability Survey, CIGRE. The working group A2 has done a survey on the reliability of transformers. They have identified that close to 37% of the failures occur at windings followed by tap changes, right? So this would give you a kind of an overview on the sheer number or the sheer components that are being affected by failures. So transformers, the windings being one of the most commonly affected part. Now, when the objective is diagnostics, right? So you need to understand what can be done to figure out what the problems are, what can be done to figure out how the problems can be solved. So those are the next steps that has to be done. So we already have a lot of diagnostic tests that are being done in transformers. We have different varieties of diagnostic tests, starting with the electrical, the oil analysis, the partial discharge analysis, simple insulation resistance measurement, dielectric response measurement, tan delta measurement, sweep frequency or response analysis or SFRA. So these are used to understand the different parameters or the different components of the transformer. So if I want to understand what is the the condition of the insulation paper, right? So we can go for advanced techniques like frequency domain spectroscopy, which gives you the understanding of the moisture in it, right? Now, if I want to go towards a more thermal approach to understand whether there are any hotspots or what is the hot oil temperature, sorry, top oil temperature in my transformers, we can go for either hotspot monitoring, temperature monitoring, or simple thermographic practices can be done. If I want to move towards partial discharges, either I can use an ultra high frequency sensor which can be installed in the transformer to identify partial discharger, or acoustic sensors which can be used to identify and localize partial discharges at the same time, right? Now we can measure the oil temperature, sorry, the oil pressures, the vibrations using vibration sensor to understand if there is any mechanical issues over there. And we usually do certain tests like dissolved gas analysis, furan analysis, BDV, acidity test to understand the oil, the nature of the oil that are being used. Now, a lot of these tests for critical transformers are being done regularly, right? So they're usually done on a time base. Now, time-based concept. Now, if there are some problems that exist with transformers or something has happened to the transformer, then we kind of use some of these tests to diagnose the transformers and diagnose the failure to understand what has happened and to understand what are the next steps that needs to be taken to repair the transformer and put it back into service. So the one key thing that was missing was, so you have your physical asset, that is your transformer, and which you have perform a lot of tests, either time based or condition based, and you have a bunch of data that is sitting and collecting with you, right? Now the understanding is that we already have a lot of transformer models, which we'll be discussing in the coming slides, and we have a set of data that is coming either from the reports that we are using or from the online monitoring systems, right? The objective is, rather than looking at the individual test results of the routine test individually to see any trends, why can't we combine a bunch of this data, perform analytics, and why can't those analytics give us what actions to be taken? So this is where the gap truly is right now, right? So we have transformer models which we use for simulation, based on which we are designing and optimizing the transformer designs. We have a bunch of data that is flowing from the transformer, that is either your online monitoring systems or your routine test reports, and you can perform a bunch of analytics to determine the trends of the different parameters. But what about the action, and what about advanced analytics such as your machine learning algorithm that can be run, which can provide you with the right action, right? So looking at this problem, the two-way link of data and action, this gave about the application of digital twins, as we call it, into the field of transformer asset management, right? So jumping into this, before going into how we use the digital twins, let's figure out what digital twins are. So what is the concept behind digital twins? So digital twins was not something that was meant for power systems, right? Like multiple concepts in power systems, this was borrowed from other domains. So to keep it very simple, but at the same time understandable, so digital twins are nothing but integrated multi-physics and multi-scale probabilistic simulation, right? So you're going to have a multi-physics simulation, since a transformer is not just an electrical device, right? It has mechanical components, it has the thermal components, it has chemical components, right? So you need to understand the different models that exist within these, and which gives you a virtual representation of a physical object. Now, this is the second part, right? So you need to have a dynamic virtual representation of a physical object, which kind of changes itself based on the situation, or by using the real-time data to enable understanding, learning, and reasoning. So this was one of my favorite definitions of digital twin, because it puts everything that a digital twin is in one single line. So a lot of people kind of confuse a digital twin with simulation. So it is not just the simulation part, it is a simulation which gives a virtual representation of, or a virtual model of the physical object, while being dynamic enough to change itself, to adapt itself based on the real-time data, which gives us the ability, or it enables us the ability to learn from the system, to reason with such systems, and to understand our system and our transformers better. So looking at this, we can see that a digital twin basically consists of three things, right? So now applying this to the transformer. So the digital twin starts with a model of the transformer, right? So it always starts with the model of the transformer. It needs an evolving set of data or to the transformer. So when it is evolving, it has to be dynamically changing. It has to be updated constantly. And there needs to be a means of dynamically updating or adjusting the model based on the data. So you have a model which you have decided, like, okay, this is going to be my transformer. You feed it some data. Now the data has to be changed dynamically, because the data is going to be a real-time information. And based on the real-time information, you're going back and dynamically updating the model as well, right? So this kind of gives you a closed loop approach of transformer monitoring. Now, in one sense, it combines certain aspects of your simulation concepts, it combines certain aspects of your online monitoring concepts, your industrial IoT concepts, but at the core of it, it is completely different you add up these two, it relates, gives you completely different concept. That is what we are calling as digital twins. So a simple example of the digital twin framework is given here below. So let me just pull out the pointer. So you're going to start off with the modeling, right? So the first thing was the modeling. So you're going to have either white box modeling, machine learning model, artificial models, or thermal models, different types of models, which we'll be seeing in the next 3-4 slides. You need to simulate those models, but the most important thing is each model gives you a different output, right? So the thermal model will give you, talk about the hotspot temperature and the top oil temperature, and its degradation can be measured using that, right? So this is just one example. Your simple circuit model will give you the currents and voltages on both sides of the transformer based on fixed resistances and inductance values. You simulate this, you end up with the thermal characteristics, the thermal responses, and this physical, at the physical level, you're going to be providing different sources of data which will be fed back into the model, and you can provide real-time ratings, real-time dynamic estimate, dynamic ratings of the transformers, reliability indices, health of the transformer, estimating the lifetime. The applications are numerable based on how you want it, right? So this is just an example of the framework that we are discussing about. So a quick look at the models, right? So there are plenty of models that are available. I'm just putting a bunch of pictures over here so people can understand. So we start off with the basic mathematical models and mathematical representation of the transformer circuit. So you solve the equations, you'll be ending up with certain currents and voltages. You're going to have circuit-based models which represents the transformer resistances, the winding resistances, the magnetic inductances and things like that. You're going to be having the unified magnetic models that are based on transients and transient analysis. You're going to have topology based models which gives you the magnetic coupling and the magnetic linking between the different windings. You're going to have simple thermal models which give you the output kind of gives you the top oil temperature and the hotspot temperature of within the transformers, right? And all of these models are still being researched on. Like, to give an idea, like the thermal model has already been established in IEEE a while back, but people are still working on thermal models. The electrical models and the mathematical derivations of these electrical models are still being fine-tuned, and the interaction between these models would is something that people are really focused on to understand how the inputs and the outputs of these different models can work together to give you a wholesome understanding of what your transformer is actually going through, right? So this image actually shows the finite element analysis or the physical model of your transformer, right? So some of the most common physics-based models are going to be your electromagnetic model, thermal models, mechanical models, and certain dielectric models. So just to give you an just to point out how much people are actually working on this, is one of our colleagues who was working on dynamic prediction of the maximal permissible transformer overloads, right? So to understand what is the thermal behavior of the transformer, so we have the thermal models. How do we make the thermal model dynamic, and how do we estimate how much we can allow the transformer to be overloaded, right? And a lot of inputs have been used, such as the tap changer position, what is the cooling equipment looking like, what is the actual measured voltages and current, right? So such models are key when you're using a comprehensive system like digital twins, where you're going to have the real-time data that is flowing at a particular speed, and you need the ability to update your models at that speed as well, right? So the next step is, so you have physics-based models, you're going to have data-driven models. Now, data-driven models are purely based on the data. They do not essentially worry about what is the physics or between the different parameters. You have a bunch of data. So the data sources will be explained soon, but you have a bunch of data, either real-time data, transformer data, analytical data, health data, whatever it is. Based on this, certain models are being created, and these models kind of interact with each other to understand or to give you a better idea of how transformers essentially behave, right? So here is just a simple comparison between the different transformer models that we have done. So one of the key thing to understand is a mathematical model and a physical model will have high computation burdens, which mean making them to work on a real-time level may not be as suitable. And whereas if you're using a multi-physics model, which is a physical model, you'll be able to get a really good understanding of what your transformer is exactly like, right? But you have a very good representation of the accuracy, but it also needs a lot of data from the manufacturer which may not be available publicly, right? Comparing that with the thermal model wherein you have a low computation burden, but it will give you only thermal representation, that is only the oil temperature levels can be determined, right? And what can be used, like for example, I can measure the degradation of the thermal insulation, I can measure or the dynamic overloading of the transformer using the thermal model. So a combination of these models will play a more important role in determining how you want to position your digital twin like. So you have different combination of knowledge based, data driven and physics based system, and wherein the right combinations for the particular use case. For example, if I want to just worry about the degradation, what is the end of life, right? So thermal model will be suitable for at a lower voltage level. But when you want a more comprehensive solution, a combination of data driven and physics based for certain applications, a combination of knowledge based and physics based for certain applications will kind of give you the right path to understand how your transformer will be behaving and how your transformers has to be maintained, right? So continuing with data sources and analysis, Mr. Dianath will be carrying forward. Thank you for your time. Dio, I think if you can take over.
Thanks, Sarvanan. So
Thank you,
participants, if you
Sarvanan.
have any queries before Dev can take over, if you have any queries, you can also feel free to drop into the chat box. So we will address it at the end. Thank you, Sarvanan. Thank you, Dev. You can start.
Yeah. Good evening, everyone. So continuing from where Sarvanan left, we know that we have already seen discussions on three types of models for digital twin: the physics-based, the data source, and the knowledge-based. The data-driven and the knowledge-based. These all depend on the kind of data that we already have for the transformers. So the data sources when a transformer is in operation can be multifold. The first comes the design data, right when the transformer is commissioned at the beginning of its life cycle. You get all the design data, and what data is important within design is the temperaturized data, the clearances data, and the overall components data. Second is the real-time data from the operation like voltage, current, loading. Then third is operational data, which is based on the events that have occurred on transformer, like through fault, intensity. Then there is the inspection data during maintenance, the data on the data on visual inspection, like what is the condition of the bushing, condition of if there is any leakage from the transformer, or condition of the main tank. Then there's maintenance data, the test records, the low voltage tests and the advanced diagnostic tests. Then there is simulation data for carrying out real-time studies, the from based on grid parameters and over voltage studies. And finally comes the external data, like what is the sort of feeder that the transformer connects to, what is the weather data, like if during maintenance, in what weather conditions does the maintenance activity has been carried out to ascertain the confidence level of the maintenance results. So these all data sources combined together to give us a condition as a platform for a transformer. Now in the digital twin analysis can be done either driven by model or driven by data. So if we compare both, data driven analysis is simpler to implement because it is dependent on the data that is already available with the utility, while model driven analysis, even though it will offer higher precision, but it will be uh, slightly costlier and also slightly difficult to implement because we don't have the specific model for each type of transformer. The data-driven analysis has a variability in test results, and there is less precision, while model-driven analysis will offer deterministic approach, and the thresholds can be accurately defined. And in data-driven analysis, it can have a component-oriented approach. Each component will have its own relevant set of data based on which we can predict the condition. While in model-driven analysis, component oriented approach is slightly difficult because we do not have a specific degradation model for each component. Currently we have only physics related models only for the whole transformer or the active part of the transformer. Now when we talk about applications of digital twin, there can be first we can see on the thermal, on the one of the most prominent applications of digital twin is to estimate the aging rate of transformer. Now aging rate can be estimated using two different kinds of model. One is thermal kinematic model, which calculates the top oil temperature and hotspot temperature based on the manufacturer data. The manufacturer data that is required is the data sheet on the temperature rise test or short circuit heat run test, short duration heat run test. Another is load profile and the ambient temperature readings. Based on that, we calculate the top oil temperature and the hotspot temperature. And based on these readings compared with the OTI readings, we calculate the aging acceleration factor for the transformer. Another model for aging estimation is aging marker model. Now this is a data-driven model where based on furan analysis and methanol analysis of a particular unit, we can derive the DP value. And based on DP value, we can find out the elapsed age of the unit, the technical age that the unit has already underwent through, and we can find out the aging acceleration, whether the unit is under accelerated aging or not. Now, when we talk about a unified condition assessment platform, generally for each transformer, in terms of database, we have its readings in an ERP or a enterprise asset management system. The operational readings are present in SCADA, and then there are design documents. Now, each transformer has its own O&M records for for component-wise O&M records like bushing, winding, OLTC, the test records, and based on which we can derive the health model. It is we have shown the data-driven model here with correlation of DP, furan, and methanol. Then there is a failure model. Failure model can take into account the previous DG history, the history of DGA or dielectric incidents in similar designed equipments in their via design correlation and implementation of bathtub model. Health, aging, and failure model can be correlated to find out a probability of failure of the equipment. And then there can be an impact of failure model. What will the impact of the failure or outage of transformer, which takes into account the feeder connections, the social impact, like where is the transformer connected, what kind of load is it serving, like if it is serving the generators or RE based plants, and the environmental impact of failure, like whether the transformer is filled with mineral oil or ester, the commercial impact, what kind of type impact is there, along with grid operator data. Grid operator data will be required to find out the grid contingencies or n-1 contingencies and the inventory data. So these together will be mapped together to formulate a risk index, and based on risk index we can derive a condition assessment. Now further, apart from these, we have indicated something and highlighted some data in dashed lines. Now these are not data driven but more towards the physics based models like thermal model, which can correlate on based on moisture and OTI readings. We can use the Emsley equation and the Deng and Wang equation to find out the aging rate of transformer. We can have mechanical model which is based on FRA or FRSL readings, the frequency response analysis or frequency registry losses. And then we can also make a 3D model of transformer. If it is a new transformer, we can utilize its BIM model, or if it is an old transformer which is already commissioned, we can utilize photogrammetry to create a metaverse of a transformer. And you utilize this along with the data driven models to formulate a digital twin. Now, if we see on application side, uh, Savan had already talked about the condition based maintenance uh, program for transformers. If we want to advance further to reliability centered maintenance, we can correlate the health and risk assessment of a transformer. And health assessment, this is a case study from Power Grid where we are using the health score and severity analysis, the age of equipment, type of bushing installed, visual checks, number of switching operations only for reactors, and then elapsed age based on aging model, the previous failure history, and DJ history in similar design equipments. The risk assessment takes into account feeder connection, loading or voltage swing issues, spare availability, and commercial impact. Now, if we now just to indicate the type of markings that we use, here it is indicated for calculation of probability of failure. So in terms of, if we can use health score with severity grading, like if the transformer is coming under high severity, it can be graded as the higher risk of failure. And if it is most of the, in terms of failure, we have seen most of the failures either happening within the first 5 years of the commissioning, or in the last in the after passing of 25 years of age, the failures have risen. So we have kept those two as the at the highest severity risk. And we have seen the transformers to be mostly stable between 5 to 20 years of age, so that has been categorized as low risk or stable. And type of bushing, various utilities based on experience have observed that OIP bushings have had a very high rate of failure compared to RIP bushings. So that is reflected here. In terms of switching of the reactors, we consider this parameter only for the reactors, not from the transformer. We have seen such reactor switching happening more than even 700 to 800 cases per year in some of the cases, mostly connected to renewable energy grid. And each switching instance causes a stress on the insulation system of the reactor. So we have suitably accommodated that in this table. In terms of visual checks, we have found the most critical points to be if the transformer bushing has a low oil level, or the MOG indicates a low oil level in the conservator. Other than that, other significant points are if the silica gel has changed color, or there is high thermovision uh, reading in the bushing, then that is also categorized as high risk. And now, based on all these above parameters, we are calculating a health score, and then we are suitably weighting it with aging model or the failure models. Like if an aging model, if the elapsed age or the technical age of the unit is coming more than the actual age, we are giving a weight of 10% higher weight over the normal health score, and similar to dielectric failure or the DGA history in similar design equipments. If we talk about impact of failures, we have given highest severity to generation linked units, or the units, those units which are being used to pull power from RE based stations or the radial feeders, because failure of units linked to these feeders can cause grid outages. In terms of loading issues, we are calculating n-1 violations for transformers, or more than 5% voltage swing for the reactors. And similarly for spare availability, if there is no spare available, that is the most critical unit. And if there is hot spare, that is a stable unit that has been categorized as a stable unit. In terms of commercial impact, we have seen more about 7% of our units having impact of more than rupees 4 lakhs in cases of complete 1 day outage. So that has been categorized as the most severe. And in terms of environmental issues, mineral oil filled unit with OIP bushings has been categorized as the most severe, because any failure of these equipments, any dielectric failure, can cause consequential damages in the switchyard. So based on this, we are formulating a risk impact assessment matrix. We are using an exponential risk matrix. And when we populated all our around 3800 transformers and reactors. Based on these parameters, we found about 70% of those units to be in a stable category, while only 1% appeared in severe category. So this was an example of a data-driven approach for creation of a digital twin. So this is not still a digital twin, but an assessment platform which, when correlated with the thermal model and the mechanical model, will formulate a complete digital twin. So the future scope is to correlate it with the effect of transients on the condition of transformers, like during switching, what is the transient observed by the transformer, the duration of the transients, and along with the simulating the physical models with the actual transformer condition, and then applying those for enterprise-wide asset reliability monitor. So this was the application part of the digital twin. If we want to have a reference reading from CIGRE, CIGRE has already published around 57 different technical brochures on transformer condition assessment and its management. So we have categorized here it under different heads, the different technical brochures. So if you want to have a brief on different types of condition assessment and how to correlate that with how to bring it on a condition assessment platform, how to uh, understand different values, we can go through any of these documents. So yeah, that was it on digital twin.
Thank you very much, Dev. Participants, if you have any queries, you can feel free to ask. So I have a few queries. If so, there was information that the failure of a transformer is quite high, around like 0 to 5 years, right? And after 25 years. So may I know, is there any specific reason why and the failure chance is high around 0 to 5 years? Because it is a brand new transformer,
Yeah,
and
so in the initial worldwide, what has been observed why the failures are higher in the first 5 years? Mostly it is due to design issue or the commissioning issues. Any if the commissioning is not proper, if there is any issue in design, mostly they reflected within the first 5 years of operation of a transformer. When the full load is given on these transformers, mostly these issues crop up during the first 5 years of operation. If the transformers survive those infancy years, then it has been seen that mostly they remain in normal operation till the end of life. And again, after 25 years, due to continuous aging of the transformer, the dielectric becomes weaker, and the failures again start rising after about 25 to 30 years of operation.
yeah.
So and if we go by statistics, if we see the statistics, what CIGRE published in around 2016, the last survey that they carried out, around
Okay.
37% of the failures had happened within the first 5 years, and then around 29% failures happened in after the end of life period, means around 25 to 30 years or even more than 30 years of age. In
Okay.
the period between 5 to 20 years, it was only 14 to 17% failures were reported worldwide.
Okay. Okay.
That was it.
Yeah. Yeah. Thanks, Dev. And another general question. So, like, so how accurate this like digital twin can be? Because like it has to be dynamic to get the inputs from the physical device
Yes.
to reflect the like same, I mean the exact condition. Because some issue it may accelerate, the issue may be like normal until yesterday, and it may accelerate, and
Yes.
some issue we may do a like a maintenance or like fix some issue and it can be solved. So how it is going to consider these two conditions. Like some issue it may accelerate, and some issue if it is getting addressed in between. So uh, yeah, so
So,
will there be any manual intervention, or everything through like a sensors and like automated system?
Digital twins will never be fully accurate. That's what we think, that because
Yeah,
I mean, if we want, we cannot say that with our option of digital twins will eliminate all the failures, because some failures are in transformers are due to sudden spikes, or means they happen suddenly. We cannot predict that with all the
yeah,
all online monitoring systems in place, all those spikes or voltage spikes on the insulation will get detected, or they will translate into a higher DGA before failure. Some many times we have seen transient cases, means transient faults causing failure of transformer within microseconds. But what we can do with digital twins can only be as accurate as the data that is coming through the sensors or offline test results. So, and that's why we have shown that digital twin is a combination of three different kind of models. One is physics based, which and which applied can be the most accurate. Another is data based. Data based will be easier to implement, but its accuracy will be slightly lesser because it is based on the empirical data, and it may not reflect the true condition of the transformer. Another is knowledge based. Knowledge based is where there is a manual intervention in knowledge based, because it is based on perception of the human, what kind of knowledge he has derived from the past condition of the unit. Now, all these three models are equally important. We cannot say that, okay, I will not have knowledge based or data driven model of the transformer because accuracy is lesser. What we can do is a transformer digital twin is a combination of different models, and we can have physics based model. Like if you want to apply a thermal model, it can be physics based because there are established relations between temperature or moisture, which has been proven, and that model can be the most accurate. But when we want to go for a mechanical model, it can be it is better to make it a data driven model, because then you can have data from multiple transformers of the same design or sister units, which can feed which can feed the data to develop a mechanical model of a transformer or a dielectric model. And then there can be knowledge based events like weather patterns or grid related conditions. So there will be some amount of inaccuracy within digital twin, and as the data grows over a time period, the accuracy will improve further, because the model will again train itself against the inaccuracies observed from the
yeah,
past.
yeah, I understand. Yeah,
Can I just want to add one thing in that, Gopal.
yeah,
So
yes,
the thing about this digital twin is that it's purely application oriented, right? So if a utility or a company wants to monitor transformers for a particular application, can I overload my transformers? Then the digital twin models which will be using, the capabilities of them will be completely different for something, let's say you're using for predictive maintenance, right? And just to give you a small case, there was one of my friends. I mean, he was also working in the same topic. He has a company which does this resilience calculations for transformers and distribution systems, right? So one of the key information that they take for predicting if there is any possible overloading that can happen or any failures that can happen was the social media data. For example, if there is a match that is happening in one of the stadiums, you know that that area is going to be overloaded both electrically as well, right? Or some event is happening, social events, birthdays, parties, or something like that. So it's purely application oriented. But in essence, the models can be tuned to deliver the right set of content, but you need to have, at this stage, you need to have checks and balances to ensure that the output is right. I just wanted to add that.
yeah, yeah. Thanks, Saravanan, and thanks, Deonath. So, participants, if you have any queries, we can
Yeah,
can
Yes, I
discuss
Gopal,
have.
further.
uh, Uh,
Hi. Hi,
Yes,
Sasi.
Rahul, you continue, please. Yeah, I let
Yeah.
Rahul
Thank
through.
you. Yeah, yeah, fine.
Yeah, thanks,
Yes,
Shashi.
Rahul.
So my query is quite similar what Gopal has asked. So this technology works on, physical data that would be provided by the person who is doing the test or at the site engineers, right? Another part is through the sensors or the real-time data through DGA. But we already have that data transferred to the SAS system or SCADA at site. So there will be a separate provision for getting the real-time data to the digital twin technology, or it will be integrated with the SAS, or is there anything already implemented at site by Power Grid or other utilities as of now in India?
Uh, s- so, if we, I can say what we are doing in Power Grid. So, you're right that most of the operational data is already integrated in SAS and in SCADA system. So, what we are doing is we are taking those readings from the SCADA itself into what we have this assessment platform that we have created. So, like the readings on load profile, the OTI readings are already we are taking from the SCADA itself. We are not connected online DGA right now in this platform. What we are taking is offline DGA readings, and all those maintenance test results along with offline DGA readings are already populated in our ERP system. So we are collecting all those maintenance and inspection results from the ERP system, the operational results from the SCADA system, and design results we are pulling in from the PDF documents. Those PDF documents are around 10 to 20 years old. So we are using NLP to extract the relevant data from those documents and to create a failure model of the transformers.
Okay, so as if now we do not have any particular, environment or setup to get the real-time data and link it with the digital twin technology. It is under progress, or maybe in coming future we'll see that, right? Currently,
Yeah,
you're taking the data and filling it, and it's
no,
not
we are not taking
working
the
well.
data and filling it. Means this data is coming in through FTP mode, and it is auto populating in our system. There's no manual
Okay.
intervention there. But yeah, if you're talking about real-time integration of a SCADA with IT, that is not happening because I don't think in this MATI, in this or CA allows real-time integration of OT and IT in India. That is not allowed. So what it is happening with in Power Grid is this data is run in batch mode in OT system. It is converted into means already some processing is happening in OT system to derive relevant values, and then in 24 hours, every 24 hours,
Okay.
this data comes from OT to IT system in batch mode.
Okay. Okay. Got it. Thanks, Devnath. Yeah. Thank you. Yes, Shashi, you can ask your question.
Yeah, thanks, Rahul. So,
Thanks, Rahul.
thanks for this session, Gopal, Saravanan, and Yonath. Thanks for sharing your knowledge. And my question is, what are the tools or softwares you are using to connect the virtual model with the physical model, real world model?
Okay, so we are still working on complete development of digital twins. So, like I said, we have only created the health model, the failure model, impact model, and the aging model. So, the tools that we used in that when we made the health model, we used AIML models of random forest along with ensembles, that is ADA boosting. When the aging model was on empirical based modeling, so no any particular means any particular software was not used for that. When we while creation of failure models, we used NLP to extract the relevant values from the design documents and then populate the data in a Excel sheet only, and that data was further correlated with dielectric failure history. Impact model was again the impact assessment was done using decision trees, and over the top of now correlating all these models, it was an analytical hierarchical uh, program was used, AHP, and normalization was done using AO Johnson transformation. The softwares for data storage were ERP, and SCADA data historian was used to extract values from SCADA system. For This was on the software part. For the photogrammetry, for this 3D models, we are still in process to make those. Means we have done some pilot projects for a couple of transformers. There we have used in one of the projects we have used Navisworks, and in another pilot we used this photogrammetry. Photo based on photogrammetry, we created a metaverse of transformer. We are still in a process of making a thermal model, so no particular software I can mention on thermal modeling right now. For mechanical models, we are in the process to develop them based on FRA readings, and there um, we have currently used there means multiple ML programs are being used there, starting from XML parsing to extract the relevant features from an FRA signature. Then we have used random forest for model building along with hyperparameter tuning. And then that model is being we are integrating COMSOL libraries to develop a mechanical model visualization. And for the final chart that you saw, that was from Power BI. So all these models together are being integrated in a backend system, and the front end we are using Power BI to visualize those results.
Okay, so that means you are using a lot of tools.
Yeah. So like I said, digital twin is not a single model that can be built. So it is a combination of different models.
Yeah, understood. But there is some tools available in market like Ansys Twin Builder. So
Yes.
if that helps you, you can use that.
Yes, we Miss Ansys is in our pipeline
Yeah,
to implement. Once we go for implementation of this photogrammetry with uh, our uh, the health models, then we have planned to use the Ansys Twin Builders. But right now, it will still take some time. Yes, I
yeah, yeah.
think we envisage around 4 to 6 months before we go for that step.
Okay, thanks. Thanks,
Yeah, I
Divya.
just wanted to add something, Sasi, that if you are going for this, I'm not talking from a utility perspective. So I think Sasi from an OEM and Devnath from a utility perspective. So one of the key things is a lot of these algorithms that I think Devnath mentioned are something that we are trying to we are implementing it in Python, right? So one of the easiest languages to implement a lot of these algorithms. Power BI is one of the easy tools, but one of the key things when we are going for something like ANSYS or Altair or COMSOL is the representation of the transformer kind of changes. Then, so if I want the winding information, the physical information parameters of the transformer, like the dimensions of your wire, the windings and the core, a lot of them are OEM dependent, right? So the OEM may not share with utilities, or they may share, or it may not be available freely also. So if you are going for something, let's say like thermal models, the development of these thermal models also will be done while the digital twin is running as well. So you kind of hope to, so the ultimate aim is that we kind of hope to learn from the digital twin, how can we, bring about a better model. So tools, yeah, there are a lot of tools. Like I think Schneider, that Aveva is one of the tools for digital twins.
Yeah,
Altair, which is very similar to Ansys, they've also brought about digital twin solutions. So everyone is bringing in digital twin solutions. But the one key thing to note about what has improved and what has motivated companies like COMSOL, Altair, and Ansys is they are very heavy models, right? It's not possible to run them easily. That simulation time is high. But what all these companies are bringing about is small and lightweight models which kind of can run on cloud systems. So that will in turn help you kind of easily, like quickly connect to your system and bring about what you can call as a digital twin. Just wanted to point that out.
Yeah. Whatever you said is true. And nowadays, most of the companies are started to talking about digital twins. Hope in another 3 to 5 years, many company will start to implement one by one.
True that.
Yeah. Yeah. Thanks, Saravanan and Dionath.
Thank you, guys. Is there any last query? We have run out of time, so if there is any last query, we can take in. Otherwise, we can wind up the session. Yeah, I think it's fine. No more queries, I think. So thank you very much, Devnath. Thank you very much, Saravanan. Thank you for this session and thank you for your time. Thank you everyone for joining. So we'll be uploading this recording into the NGN site, and we'll share you the link later on. Thank you, everyone.
Thank you. Thank
Thank
you,
you,
Gopal.
everyone.
Yeah, thanks, Gopal.
Bye bye.
Thank you all.
Thank you. Thank you.
Thank you all.
Thank you. Bye.